Welcome to today's Explainer. We're skipping the casual stargazing today and diving straight into a literal cosmic time capsule. You see, in astrophysics, not all star groups are created equal. Some of them are just perfectly positioned in their life cycles. They act as these massive astronomical yardsticks, tools that actually help us decode the fundamental laws of the universe. And today, we're unpacking one of the absolute most fascinating yardsticks out there, a star cluster known as Caldwell 28.
Now, to find this cluster, we've got to look way beyond our own solar system. We're traveling a staggering 1,470 light-years away, pointing right at the Andromeda constellation. Just pause and think about that scale for a second. The light we're capturing today from this cluster, it actually began its journey toward Earth almost a millennium and a half ago. It's this incredibly distant, ancient laboratory, but surprisingly, it holds the answers to how stars right here in our own galactic neighborhood actually behave. But hey, before we get completely lost in the heavy astrophysics, let's ground this in a little history. This incredible cluster wasn't spotted by some billion-dollar modern space telescope. No, it was actually first discovered way back in 1783 by the pioneering astronomer Caroline Herschel. For literally centuries, it was just this beautiful kind of enigmatic smudge in the night sky. It's really only recently, with the kind of modern data we have now, that we've truly started to unlock its secrets.
So here is our flight plan for today's Explainer. 1. Meet Caldwell 28. 2. A benchmark star cluster. 3. The lithium mystery. 4. Stellar clocks and rotation. And 5. Binaries and white dwarfs. All right, jumping right into section 1. Meet Caldwell 28, a stellar neighborhood.
So, what exactly are we looking at here? Well, Caldwell 28 is what we call an open cluster. Think of it as a loosely bound group of up to a few thousand stars that all formed from the exact same giant molecular cloud. And because they sprang from that same cloud, they share roughly the exact same age and the same initial chemical recipe. Now, for Caldwell 28 specifically, we're looking at a neighborhood of about 302 confirmed member stars. It's essentially a massive family of stars, all born together, just drifting through space as a pack.
Moving on to section 2, a benchmark star cluster, the Rosetta Stone.
Now, you might be wondering, out of the thousands of clusters out there, why is this specific one our Rosetta Stone? Well, the secret is entirely in its age. Caldwell 28 is an intermediate age cluster, clocking in right at 1.3 to 2 billion years old. See, in astronomy, we've got tons of data on really young, hyperactive stars, and plenty of data on super old, quiet ones. But that transition period, those awkward teenage years of stellar evolution around the 1 to 2 billion year mark, those are way harder to study. Caldwell 28 is kind of the missing link. It is perfectly aged to help us test theories about how stars evolve, how they age, and how they eventually slow down. As the researchers put it, NGC 752, which is just Caldwell 28's official catalog name, could become a benchmark cluster for studying stellar rotation and activity right at that 1 to 2 billion year gap. By studying this cluster, we're basically building a cosmic mirror. We can take the baseline data from Caldwell 28 and use it to measure and understand the lifespans of other stars scattered all across the universe. And yeah, that absolutely includes trying to figure out the deep history and the ultimate future of our very own sun. Which brings us to section 3, the lithium mystery, chemical clues.
Okay, this leads us straight into a massive, honestly head-scratching puzzle involving a pretty fragile element. Lithium. You see, as a star ages, its internal mixing churns lithium from the surface down into the blazing hot core, essentially destroying it. Now, astronomers naturally expected this to be a nice, smooth, predictable process. But older clusters, like the Solar Age M67 cluster, actually show a large, totally chaotic spread in lithium among very similar stars. Yet, look at Caldwell 28 over there on the left. It shows this super tight, really neat lithium distribution among its solar-type stars. So the million-dollar question, why is one so chaotic and the other perfectly uniform?
Well, to figure that out, astronomers looked at iron. The younger Hydes cluster has pretty high iron, but Caldwell 28, it sits at a value of plus 0.01. For us non-astrophysicists, that basically means its iron content matches our sun almost exactly. And this is a huge revelation, because Caldwell 28 shares this exact solar metallicity, but completely lacks that chaotic lithium spread we see in older clusters. It proves a major point. It tells us that metallicity variations don't actually drive wild changes in lithium depletion after a certain age. So that chaos we see in older stars, it has to be caused by something else entirely.
The plot thickens, right?
All right, let's look at Section 4, Stellar Clocks and Rotation, Measuring the Spin.
Beyond just chemical clues, Caldwell 28 is acting like a stellar clock, helping us understand exactly how fast stars spin as they age. But researchers really have to play detective first here. I mean, you can't just point a telescope at the sky and assume every single star on the frame belongs to the cluster. No way. They have to use incredibly precise velocity data to sift out the true cluster members from all the distracting background and foreground noise. But once they finally isolate that pristine list of genuine members, then they can get to work accurately measuring their spin.
And once they did isolate those members, they found a seriously startling contrast. Your normal single stars in Caldwell 28 are rotating pretty slowly, less than 35 kilometers per second, which is exactly what you'd expect for stars that are 2 billion years old. They're taking it easy. But then look at the system called DS-and. It is spinning at a blistering 105 kilometers per second. Why the massive difference? Well, it's because DS-and is a binary system. It's two stars orbiting in very close quarters. And this beautifully illustrates how being in a tight binary relationship can radically speed up a star's rotation, literally overriding the normal slow aging process.
And that brings us perfectly to Section 5, Binaries and White Dwarfs, Unlocking the Extremes. This whole discovery of fast-spinning binaries pushes us right into our final phase of investigation. Let's zoom in on DS-and for a second. This is an eclipsing binary, meaning the stars actually pass directly in front of each other from our point of view here on Earth. And that setup, it acts as a totally perfect astrophysical laboratory. Just by precisely timing these eclipses, astronomers have pinned down their exact physical measurements. We're talking a primary star mass of precisely 1.692 solar masses, and radii measured down to the exact thousandth of a solar radius. Having measurements this unbelievably precise is exceptionally rare, and it gives us an ironclad test for our stellar evolution models at that critical 2 billion year mark. But believe it or not, eclipsing binaries aren't even the most extreme objects hiding in this cluster. I actually want to ask you a question to quickly recalibrate our focus here. What happens to the absolute oldest, most massive stars in Caldwell 28? I mean, the ones that totally burned through their fuel way before hitting this 2 billion year mark. What exactly remains of them today?
The answer is actually pretty thrilling, because even after billions of years, this ancient cluster is still hiding some completely brand new secrets. Recent deep surveys of Caldwell 28 have actually uncovered some incredibly exotic stellar remnants. We're talking extremely low-mass white dwarfs, which are basically the dead, super dense cores of former stars. But maybe even more fascinating than that, we're finding these mysterious objects dubbed blue lurkers. These are stars that appear way hotter, much bluer, and way younger than they have absolutely any right to be at 2 billion years old.
And the real smoking gun is right here in the data. Just look at stars 9, 13, and 16. These are our blue lurkers. They are blazingly hot, sitting anywhere between 6,500 and 6,750 Kelvin. But check out that final column. Every single one of them is in a binary system. Astronomers are now pretty convinced that these stars only look so young and vibrant because they're literally siphoning material away from their binary companions. They are essentially stealing their partner's life force to artificially rejuvenate themselves. It's wild. And these specific hot evolved stars are actively forcing us to rewrite the rulebook on late-stage stellar evolution. So, when we step back for a second and look at everything Caldwell 28 has taught us, from crazy stellar rotation to vampiric blue lurkers to the whole lithium mystery, you really start to see its true value. Remember that chaotic lithium spread we talked about in older stars? Well, thanks to the incredibly pristine data we get from Caldwell 28, researchers are now concluding that this chaotic spread might actually be the exception rather than the rule. This single, distant cluster has pretty much proven that our previous assumptions were wrong, forcing us to completely rethink how stars mix their chemicals over billions of years.
It really makes you stop and wonder about the sheer scale of what we still don't know, doesn't it? If Caldwell 28, just one single 2 billion year old cluster located 1,470 light years away, is still out there revealing hidden white dwarfs, life-stealing binaries, and totally upending our chemical theories, what kind of secrets are hiding in the billions of other clusters scattered across our Milky Way? The universe is just this unbelievably vast ancient laboratory, and guys, we are barely scratching the surface of the results. Thank you so much for joining me on this explainer, and as always, keep looking up.